This video is on how to do regression analysis in Quantum Excel. It is part of a series of videos on DOE, and there's a link in the description to the series description page. I've already collected the data for the DOE. As you can see, I've done a central composite design. I have the two inputs, firing angle and cup rotation angle, and I have two outputs, which is the red distance and the blue distance. Notice that I have entered the spec limits as well. To run the regression, I click on the QXL DOE ribbon, then I click on Analyze Design, and then Run Regression. In this case, both of the outputs are quantitative, and so when running the regression, you're going to get ordinary least squares regression. If I had a binary or nominal output, then Quantum Excel would automatically run binary or nominal logistic regression. When I click on Run Regression, Quantum Excel is going to calculate the regression table for me in a new tab entitled Regression. By default, the regression is done in coded units. The factors area and the prediction area I will come back to in a moment, but the regression table is directly below. If I zoom way out, you can see that there is, for the red ball, a regression table for the Y hat and for S hat, and for the blue ball, there's a regression table for both Y hat and S hat as well. The Y hat model is calculated in the standard way all software does regression analysis. The S hat model comes from this column S. The S column is calculated by calculating the standard deviation of the row when the inputs are the same. So for example, when firing angle is 110 and cup rotation angle is 0, I had 4 replicates. The standard deviation that's calculated here, 0.816, is just the standard deviation of those 4 numbers. So for each one of the rows in the DOE, I have a calculated standard deviation. Quantum Excel then uses that standard deviation column as the dependent variable, and that is where the S hat model comes from. The model has the name on the far left column. So for example, the firing angle main effect and the cup rotation main effect. Then there's the two-factor or two-way interaction. And then there's the quadratics. This is firing angle squared, and this is cup rotation angle squared. To the right of that is the factor designation. The constant, sometimes called the intercept, is in the first row. Then the main effect firing angle with the letter designation A, and cup rotation angle with the letter designation B. After that are the two-way interactions. So the firing angle cup rotation angle would be the AB interaction, and then firing angle squared would be A squared, and cup rotation angle would be B squared. The columns then display the coefficient. So that's the resulting coefficient from the regression analysis. SE stands for the standard error. T is the T statistic. P is the resulting p-value. The VIF is the variance inflation factor. It's a measure of orthogonality. And the way that I reduce the model is I uncheck a box in the in model column, and then I run the regression again. Below that are the model statistics, such as R squared and adjusted R squared, the standard error, the F, and the lack of fit statistics. If I scroll to the right, you see similar information for the S hat model for the red distance, and then there's the Y hat model for the blue distance, and then the S hat model for the blue distance as well. The p-values, which are typically used to reduce the model, are color-coded. So when a p-value is less than 0.05, it is color-coded red, as these are currently in the regression table. If the p-value is between 0.05 and 0.1, then they're color-coded blue. An example of that is over here in the Y-hat model for the blue distance. We can see that the AB interaction has a blue p-value of 0.07 because it is between 0.05 and 0.1. And then finally, any p-value that is greater than 0.1 is color-coded in the default font color, which in this case is black. If I want to reduce the model, for example, if I want to reduce this AB interaction, then I want to remove the checkbox in the end model. Then I click on QXL DOE ribbon, Analyze Design, Run Regression again. And when I recalculate the regression, what you'll see is I get a new worksheet. So there's a new tab in my workbook called Regression 2, and now the AB interaction has been removed from the Y-hat model for red distance. The area above the regression table is where we do prediction. So you can see that the factor names are designated in the far left-hand column, then the factor letter designation, A, B, etc. The range of the DOE is displayed to help you remind you what the range of the DOE is. And then the set point is where I can enter the X values or the independent variable values so that I can understand what the prediction will be for each one of those set points. On the right-hand side is the prediction for both the red y-hat and s-hat models and blue y-hat and s-hat models. So for example, if I wanted to know how far the red ball and blue ball will go, if I set firing angle to 130 and cup rotation angle to 90, I would type in 130 and then 90. This is now telling me that the red ball is predicting to go 624 units and the blue ball is predicting to go 525 units. And then it also gives me a prediction of the standard deviation as well. In order to get an accurate estimate of the standard deviation, you need to reduce the s-hat model, which I did not do, but it is possible to reduce the s-hat model and get a prediction for the standard deviation as well. Below the prediction of y-hat and s-hat are the prediction intervals. So the prediction interval lower and upper is calculated as y-hat minus 3 s-hat, and the prediction interval upper is y-hat plus 3 s-hat. Below that are the spec limits. The spec limits were entered already at 670 and 630. Those are actually not defined here. These are just a reminder of where your spec limits are. The spec limits are defined back on the design sheet, and you can see that that is where I enter the spec limits for the red ball, and this is where I enter the spec limits for the blue ball. Finally, we end up with a calculation of a prediction of CP, CPK, and defects per million. So, for example, there is the prediction for CP. With a current value of 130 and 90, CP is currently predicted to be 3.7, and the CPK is predicted to be at negative 0.9. The way that calculation is performed is that the equation for CP is typically the upper spec limit minus the lower spec limit divided by 6 times the standard deviation. However, in the case of the DOE model, the standard deviation is replaced with s-hat instead of the actual standard deviation. So we're using this value, this predicted standard deviation, for the CP. Additionally, the equation for CPK is typically the minimum of the upper spec limit minus the mean divided by 3 times the standard deviation, or the mean minus the lower spec limit divided by 3 times the standard deviation. But for CPK prediction, I'll put a CPK hat there. I should put a CP hat as well. We're replacing X bar with Y hat and this X bar with Y hat. So this will be the predicted values for Y hat. And then we're replacing S with S hat as well. Instead of it being an actually calculated CPK, it is a CPK hat. It is a predicted CPK based upon the values in the model. And then finally, this defects per million in Quantum Excel will calculate the predicted defects per million by using the predicted values of the mean and the standard deviation along with the spec limits. So if I change these values on set point, what you'll notice is that all 3 of these will change. And the reason these will change is because they're based upon the mean and standard deviation, and the mean and standard deviation change. So for demonstration purposes, I'll change this to 110 and then this to 0. And you can see that now we get very different values of CP, CPK, and defects per million. Quantum Excel will also color code when you start to extrapolate. So for example, if right now I'm at 110, which is the low end of the DOE, if I was to go down to 109, Quantum Excel will still predict that value. So it's now extrapolating outside of the experimental range, but you can see that Quantum Excel now indicates that you're extrapolating by coloring that as red italics. There are tooltips inside of Excel that help you understand all of the statistics. For example, if I was to hover the mouse over the variance inflation factor, it tells you that it's a measure of multicollinearity. If the VIF is 1, it's orthogonal. And if it increases from 1, it has higher correlation with other terms. So this being a orthogonal design, the variance inflation factors are all 1. And that is how you do regression analysis in Quantum Excel.